you're looking at that, so you're going to have your container and you're going to have a liquid. That liquid can be something that's molten, so you just melt, it's just a plain liquid. So if you see L, then you know it's a molten substance. And if you see AQ, then you know it's dissolved in water. So please remember that if it's dissolved, like I said yesterday, you need to remember that it has water as well. So when we're looking at that competition at the cathode, for oxidation and reduction to see which substance is winning, you need to include water as well. And in the non-spontaneous reactions, water often does take a part in the reaction. It's sometimes one of the most important reactions. So now when you have, and that's why that first definition is here again, this liquid must be something that can conduct electricity. So you needed to remember the definition of an electrolyte for this, because you need free ions that can move around to conduct electricity for us. And these are the two ways you can get them to move around. You can either melt them, your ionic substance, or you can dissolve it in water. So you always, but then once you've done that, once you've decided what substances you have, the rest becomes exactly what we did yesterday. So yesterday is the basics of how to use the table, and then you're going to just apply it to all these things. So now you're going to look, what do I have here? You're going to have some ions in here, or you can have substances that are on the red label, or it can actually be a gas as well. But gases are more for spontaneous reaction, so it can be ions, can be gas, cannot be solid, because solid does not conduct electricity. Now here you need to be very careful. In the solution, in the electrolyte, the positive and negative particles swimming around must be ions. So ions, please, very important, they must swim, so it means they must be moving around, or they must be stuck in an ionic lattice, so positive, negative, positive, negative. So the particles that are moving in the liquid will always be ions. You can never get ions that moves through a metal, because if you use the wrong word, then you're going to lose a lot of marks. So electrons, yes, move here from the battery. So if you're thinking that's the positive side of the battery, electrons are going to be moving in your wire here, in your electric wire. And if that's the negative side, you can see electrons are going to move away there from the negative side, and it could go, if it's a closed circuit, it could then move. But now electrons again, on the other hand, cannot swim. They cannot move through liquids. They move in the metal, and then they are transferred to these ions that are now swimming around in this liquid. So these things are just ions swimming around. So now what happens, always the positive ions will be attracted to the negative electrode. But we don't just stick our copper wire into the liquid. We use a piece of metal or carbon. So there's always going to be something here that connects your battery to your liquid, and something here that's going to connect your battery to your liquid. And those are the next definitions that were there on the sheet yesterday. So these are called electrodes, and according to the ions that moves towards them, these ions are then going to determine their name. So if you remember back, you called the ions cations and anions. What were the positive ones? Cations. And where will the positive ions be attracted? To the negative or the positive? To the negative. So the cations are attracted to the negative electrode, and so it's the cation. And therefore we're going to call this electrode the cathode, because the cations are attracted to the cathode. And then the same on the other side, or almost the same on the other side. You've got the positive electrode, so that means the negative ions are going to be attracted there. What were the negative ions called? Anions. So that means the anions will be attracted to the anode. Okay, so that's where, so those are their names, but that is not how we define them. We define them according to the reaction that takes place there. So we define the anode according to what's going to happen at the anode, and we define the cathode according to what's going to happen at the cathode. Now, before we even look at real reactions, I just want you to make sense of it, because if a negative goes there to the positive one, what's it going to do? So you have something that is negative because it has extra electrons. Now it moves to the positive. So will it gain or lose electrons? It is negatively charged. It has extra electrons. So what do you think it would rather do? Give electrons or take more electrons? Yeah, so it will give electrons. So the negative ions are going to go there to the anode, and they are going to give electrons to the anode. Because they are giving electrons, it means they are losing electrons. And what do we know? What is going to be the loss? Is loss of electrons. Remember our acronym? Yeah, oil. So it's oxidation is loss. So here we go. So that means at the anode, we're always going to have oxidation happening. Whether it is spontaneous or non-spontaneous, it doesn't matter. That is how we define the anode, because that is what will always happen at the anode. Oxidation always happens at the anode. So electrons will always be lost at the anode. Then when we go to the cathode side, the cathode is negatively charged. So there you can already see electrons going to move away there. So electrons are given to the positive ion. So electrons, if I have a positive ion there, the electron is going to move onto the positive ion to make it neutral. So it's gaining electrons. So is gain. So what are we going to put here? And R for reduction. Perfect. So reduction is gain. So that means at the cathode, I'm always going to have reduction happening. And that is, if you go back to the beginning of the chapter, you'll see that is how they defined the cathode and the anode. Yeah, remember the SAGs is always at the beginning of these chapters that I'm sending you. So you can see anode is the electrode where oxidation happens. Cathode is the electrode where reduction happens. So we've made sense out of it now, but there's also another acronym that they use for that. I think the picture is here somewhere. Yeah. So you can see that so reduction is going to happen at the cathode. So it's red cat. So that's just the way they try to help people remember it. And anox. Anode is where oxidation happens. Reduction happens at the cathode. So if you want to use it. I always, for me, I don't know, it's not, you can use this, everyone uses it, but you can also see that they both start with a consonant. So red cat, and these are both vowels. Anode, oxidation, they both start with vowels. So whatever makes it easier for you to remember, just remember those two things. Sorry, I'm on duty, so I can't turn my phone off today. I'm just going to turn it on silent. All right, so there we go. That's then the anode and the cathode. So now all the reactions, we're going to kind of do the exact same thing. We're going to look at what do we have, and we're going to look at our table. I think I still have it, yeah. We're going to look at our table and we see, okay, what's happening? What is our reduction half reaction? What is our oxidation half reaction? And we're going to do exact same thing as what we did yesterday. So I always say, trust the table. The table will show you what to do. Now, if we look at this one, the molten, as soon as you see molten, it actually makes your life easier because you don't have to worry about water. So all you do is look for the ion. So they, in this question, they say we've got molten lead bromide. So the picture is basically telling you what ions we have. If you didn't know, remember, the 2 points to the fact that lead has a 2 plus charge. That's why our ions are Pb2 plus ions. Bromide, because it's in group 7, will have a -1 charge. Okay, so that's what we have. We have only that. So if we go and look at our table now, I know the answers are right there, but I want to show you that still the table works beautifully, because now we've got lead and we've got Br. There's lead. Okay. So if we look at our table again, you can see there's lead. Pb is, I can't say lead, I should say lead ions. All right, as I said yesterday, it's very important what terminology you use. So there's my lead ion, and that's, you can always look if there's another one. I don't think there's going to be another lead. And then we've got Br minus. There's my Br minus there. So those are the two things we have. Can you see how easy life is now? Because we only have one on the left and we only have one on the right. So that makes it very easy for us. So all we have to do is decide which one is reduction and which one is oxidation. So reduction is gain. So that's going to be the gain of electrons. Oxidation is loss. That's going to be the loss of electrons. But even if we forgot, you know that the oxidizing agent is going to be the one that undergoes reduction. So the oxidizing agents are all on the left-hand side, like we said yesterday, and therefore it's going to happen, it's going to go from this side to that side. And you can just go and write your reaction, Pb 2 plus, you copy it exactly like it is from the table, forms Pb one-way arrow. And the oxidation one, you're going to write from the right to the left. So you're going to say Br minus. Now you do put the 2 because it's balanced it for you already. Plus, oh, sorry, not plus. 2 Br minus. And you can see why it's 2 Br minus, because we know that Br is diatomic and it has to form Br2. And that's why we need 2 Br ions to form Br2, but that means that it's going to give off then 2 electrons. And this one is, again, I'm going a little bit fast because this one is pretty easy, because you can see 2 electrons are given off and those 2 electrons are going there, so they're balancing out. So we don't have to multiply anything, and we can go and write our net ionic equation again. And we just put everything that's on the left-hand side on the left, everything that's on the right-hand side on the right, with our arrow in the middle. So what we're going to have is Pb2 plus 2Br minus forms Br2 plus Bb. Normally you're going to form neutral substances. So you're going to have the ionic substance being split up back into the elements that actually made them in the first place. So this is a way of taking an ionic substance and getting those original substances out of it. Electrolysis, or this type of reaction is called electrolysis, is often used in the industry to, like if this was ore, you could get lead out of it. If this was a rock, that is a mixture of all kinds of things, and you'll see later on we're going to do applications of that. So there's our reaction done. No spectator ion, nothing, because it was molten, and those are the only things we had. Does this one make sense? Okay. So now you can see, because we know our ions, because we know our table, and oh no, that line is doing a weird thing. We can immediately, like they said here, we'll do one now that doesn't have the answers. The lead ions, please remember, we don't look at the products. The lead ions will be my oxidizing agent, and the bromine ions, and I actually spoke wrong there, I must say bromide ions. Remember, when the halogens becomes ions, we put a DE at the end. So the bromide ions is going to be my reducing agent. Okay, so now we can actually go and do one. So this one isn't done for us. So this is copper chloride. So we can quickly look at this one. Yes, until the battery is flat. So yes, absolutely. So that's where the electrons come from. So they're coming from the battery. They move from your battery into the solution, or remember, we still need a closed circuit. So the electrons go out of the battery on the cathode side, and they go into the battery on the anode side. And that is what still gives me a closed circuit. So remember, for electricity to happen, there still needs to be, for electric circuit to function, there still needs to be a closed circuit. So out at the cathode, in at the anode. Yes. So you can see here again, we've got a battery with a positive and a negative. So you can see here on this side, on the negative side, electrons will move into the cell, in here, and then out here, going back. So because electrons are being given off on this side, so the substance is going to gain electrons. So here you can see reduction is gain. So the chemicals will gain an electron. The battery is losing an electron, but the chemicals is gaining an electron. So reduction is gain, and therefore it's happening at the cathode. Red cat. So a reduction at the cathode. Here electrons are going into the battery. So the battery is gaining electrons, but the chemicals are losing electrons. So again, oxidation is loss. It's losing electrons on this side. So oxidation happens at the anode. Does that make sense? Okay. So now again, because they say molten, we know we don't have to worry about water. So we're just going to look at what we have. And if we have copper 2 chloride, what are we actually going to look for in that table if they give us copper 2 chloride? Remember, you always have to split up your ionic substance into the two ions that you're going to actually look for. So what are we going to look for? Perfect. And Cl minus. Nice. Now we can go and find them on our table. Cu is just about there, so yeah, so it's nice and low, so we could have them all here next to us. So if you're looking for Cu2 plus, please make sure that you again find all of them if there are more than one. For Cu2 plus, I think there is only one now. There used to be another one. Not there's only the Fe. So here you go, there's your Cu2 pluses, and then Cl minus is here. The 2 is just there because they balanced it for us, since we need to form Cl minus. Also, okay, I'll talk about that now. Just also be careful when you read the question and they ask you about the products, but I'll talk about that now. So here we can see oxidation, half reaction, reduction, half reaction, net ionic, oxidizing agent, reducing agent. You'll see after you've done a few, it almost becomes boring because the questions are often structured in this way. Sometimes they only ask for one, oxidation or reduction, because it's kind of the same skill, and then they ask you for the ionic. But I always say, please go and write oxidation and reduction half reaction, because you'll see later on there's a lot of other questions that you can do once you have those two reactions. So which of those two things are going to be okay, let's do it the way they do it here, that you don't get used to a certain pattern. Which one will be the oxidation half reaction? Perfect. So we're going to write it exactly from the table, from the right to the left. So you're going to say 2Cl minus forms Cl2 plus 2 electrons. If the question doesn't ask for phases, you don't have to put the phase. But no one's going to mark it wrong if you copy it directly from the table and you actually do put the phase. So you are allowed to put the phase there. Then, yeah, the copper is then obviously going to be our reduction half reaction. So we're going to write Cu2 plus plus an electron, not one electron, I think there's two, plus two electrons forms Cu. And there it is. Now they want the net ionic equation. So what's my next step? Cancel the electrons. So if they have the same on each side, it's easy for us. Oops, sorry. It's easy for us. We can just say, oops, I'm cancelling the coppers. Electron, electron gone, because 2 is given, and those 2 are taken up by the other substance, which is absolutely fine. So we can write everything. It doesn't matter which one you put first. 1 plus 2 is the same as 2 plus 1. So you're just going to say Cl minus, 2Cl minus, because that's what we have there, plus Cu2 plus gives us Cl2 plus Cu. And what would you say the oxidizing agent is? Okay, because it's the one that is reduced. So Cu2 plus, and if they say name the oxidizing agent, please remember that you're going to write copper ions, because if you just write copper, they will mark it wrong, because copper is a product. So read your question nicely. If they're asking for the product, then you would say copper is a product. And the other product is going to be chlorine gas. So there you're going to be very specific that it's the product is chlorine gas. And the reducing agent, what would you say the reducing agent is? Okay, so you can write Cl minus, and if they say name the reducing agent, good. Be very careful not to write chlorine. So chloride ions. Actually, if you just write chloride, it would be fine, but just make it easy for them to give you that mark. Okay, so that's that question. Do a little bit at the bottom. So what they tell us here is actually important. So they can, like I just said, you can then take an ionic substance and get the elements back out of it. So this is for an ionic substance. It can actually happen for some covalent substances as well. So mostly ionic substances, but you'll see it could also happen for water. And we'll look at that reaction because it's one that is quite important. And then always electric energy into chemical energy. And you have to have substances moving in solution. So if it's an ionic substance, it has to be an electrolyte, which means that there has to be free ions that can move. Okay, and the positive electrode attracts the ions, so that it can give off the electrons. Remember, so that's exactly what we said earlier. So this is just a summary of what I did in that very first picture. Alright, this we spoke about, red cat and ox. Okay, so this is just, all these things is just a summary. Oxidation is always the anode, reduction is always the cathode. Okay, so we've gone through that. So now, if we look at this one, so last one for molten substances, we can quickly do it. So you don't have to always have a diagram. They can just say, give the equations, and they say net ionic of this electrolysis. So if I have Au, I'm going to have to just fetch my table quick for us. If I have those substances there, what am I going to look for on my table this time? Perfect. Au3 plus and Cl minus. Okay, so we can do this one pretty fast because I think you're getting used to it now. So we're looking at Au. Au is there. And Cl minus is there. And if it's molten, I don't even have to care about which one is winning and which one is losing because it's the only thing I have. So it is going to be the strongest oxidizing agent and reducing agent. So I can just go straight into my half reactions. So they want the oxidation half reaction they want the reduction half reaction, and they want the net ionic or the balanced ionic equation. All right, so let's see. Oxidation. Which one is going to be oxidation? Perfect. So you copy it from the table. 2Cl minus, one-way arrow from the right to the left, forms Cl2 gas plus 2 electrons. And then for the Au3 plus, now we have, so the other one is going to be reduction. So that's going to be our Au3 plus 3 electrons is going to give us Au. So now this time we've got a little bit of a problem because our electrons are not the same. So the one is giving off, the chlorine is giving off 2 electrons, and gold needs 3. So what am I going to do? Perfect. So we're going to times this one by 3, which means if you're going to do it like this, do it very lightly in pencil, because they still give you marks for your oxidation and your reduction half reaction. So don't scratch it out totally. Do it lightly in pencil. So this will become 6. This will become a 3. And this will become a 6. And you said this one by 2. So this is going to become a 2. This is going to become a 6. And this is going to become a 2. So now we're happy because now we can see that this one is giving 6 electrons. And this one is taking 6 electrons. So the electrons are cancelling each other. And now we can put our arrow and say, what is left on the left-hand side? We've got 6 Cl minuses plus 2 Au3 pluses. It's going to give me 3 Cl2 plus 2 Au. So now you can see this, doing redox or doing the half reactions gives us a way of balancing an equation in the ionic form. So they can go and say, oh, go and add back the spectator ions, and you can do that. Oh, this one doesn't have spectator ions because it wasn't in water. But so they sometimes, not really often, ask you to add back the spectator ions. But that's our balanced equation. Quickly tell me, what is the oxidizing agent? Good. And what is the product at the cathode? So I want to show you that all these questions can be answered from these two half reactions. If you use your anox red cat thing, where does oxidation happen? At the anode. Where does reduction happen? At the cathode. Now once you have that, which you also get straight from your half reactions, and I ask you the question now and say, what is the product at the cathode? Can you answer it now? Yeah, it's going to be gold. Yes. So please remember, if they say name the product, you can't say Au. You have to say gold. And if they say what is the name the product at the anode, you also can't say Cl2. You have to say chlorine gas. So be very specific if they say name. If they just say identify, you can actually use either one. But then I would write the name and the symbol so that you make sure you get that mark. Okay, so that's molten substances. That's when we don't have water. So look out for that. And what that would be is that you'll just have an L behind your substance. There's no water. But then we have to, so these ones you can go and practice if you want. So these are going to be all of the same. Are you happy that we move on to water? Okay, I think those ones are becoming easy now. So now we're going to look at, but what now if it is molten? Oh, not molten, it is dissolved. So when you see the AQ behind the substance, then you know that there is water. And water can actually also be electrolyzed. So water can gain electrons or lose electrons. Like I showed you yesterday, they are in the half reaction. And therefore we have to actually look at water as well. So the first thing we're going to look at then is if I have water, just water, what can actually happen? So the electrolysis of water is a thing. It could happen. You can send a current through water, and I think you did it, some people did it in lower grades, some schools, where you actually send an electric current through water. You get oxygen gas and hydrogen gas that the water was made of, and you can actually test them. And the one will explode with that popping sound, the hydrogen, if you remember back to lower grades. Hydrogen, the test for hydrogen is that it explodes with that popping sound. And oxygen will make a glowing splintery light. Can you remember those? Okay, so you did do them in a lower grade. All right, so now if I look at water, now remember I said to you yesterday there are actually only 2 water reactions that we are going to look at, because they are going, doesn't matter what else there is. Sorry, I just want to make the table big enough so that we can see both of them. So this would be the one water reaction. There's the water there that only has electrons. So remember, we're not going to use this water because it needs oxygen and we don't have oxygen. So if we have only water available, that means, so I have my beaker, and in my beaker I only have water. So no ions, just water is in my beaker, and I connect it to my electrodes, like we said, and the short one to my electrodes. Now we look what happens, because now we don't have ions that can be attracted, but water also wants to give electrons and take electrons. So I still have my positive one. My positive one is where it wants to take electrons. If it wants to take electrons, remember, is gain. What is going to happen here? If it's gaining, reduction. Reduction is gain. And on the negative side, it wants to give off electrons. Oh, wait. You were kind of right. I wrote it the wrong way around. I said is gain, but it's the battery that's gaining electrons. The chemicals is losing electrons. So that is perfectly right. It is lost. So what you said originally was right. So oxidation is what's going to happen here, because the chemicals are losing electrons. On this side, the battery is going to give off electrons to my chemicals. My chemicals is going to gain electrons, so it is gain on this side, and that is reduction. Yes. Okay, so you can always sort it out like that. So oxidation happens at the, what are we going to call this electrode here? Anode. So my anode is going to be the one that's connected to my positive. Don't learn it that the anode is the positive one, because it is not true. Anode is where oxidation happens. That's how we define it, because it works always. Anode is only positive in a non-spontaneous reaction. It's only connected to the positive in a non-spontaneous reaction. But it's always the electrode where oxidation happens. And then reduction happens at the cathode, and that's always true. But don't again learn that it's negative, because that's again also only for a non-spontaneous reaction. Okay, so now we have basically everything, but now we need to go and look. All right, I've got water. This is the water I didn't want. This water is not going to happen because I don't have oxygen. And if you look further, you'll find no more waters on this side. So I know this gaining of electrons is the reaction that's going to happen. And if I look for my waters, remember there are these waters as well. There's a lot of waters. But all those waters need other things. This one needs NO2. This one needs NO. This one needs Mn2+. And I have none of that. I only have water. So now I'm going to find the ones that only has water. And that is going to be this one here and this one here. And because I'm looking for the strongest reducing agent, the one that would rather be oxidized is going to be this one. So now I have my two half reactions. And you see what I said yesterday, sometimes it's the same substance that gets oxidized and reduced. And this is the first example of that. There's the same substance being oxidized and reduced. So I'm going to write my oxidation and reduction half reactions. Which one will be oxidation, the top or the bottom one? Remember, oxidate, these ones, reducing agents, will get oxidized. Yeah, so that means this one here is going to be the oxidation half reaction, because reducing agents would rather be oxidized. So this one here is going to be my oxidation half reaction. So I'm going to write it the wrong way around. So 2H2O forms H2O2. Exactly. It is that one. I even marked it there. Yes. So that's the one we're going to write down, not the one at the bottom. Yes, so it's going to be 2H2O is going to form O2, and that's why I said earlier it's the test for oxygen that you're going to use here. So that's going to be O2 plus 4H plus 4 electrons. Absolutely. So that's your oxidation half reaction. And then the reduction half reaction, we don't really have choices there. There's only the one on the left hand side. So our reduction half reaction is going to be 2H2O plus our 2 electrons. That gives us H2 gas plus 2OH minus. Now what am I going to do? What's our next step? Perfect. Because I need to get the electrons the same again. So I've got 4 electrons there. I've got 2 electrons there. So I'm going to do it lightly in a pencil. And I'm going to say this one becomes a 4. This one becomes a 4. This one I added 2. This one becomes a 4. And now I can I can write my balanced ionic equation. When it's the same thing on the same side, you can just add that. You're not going to write 2H2O plus 4H2O. You can, but then you still need to simplify. So you need to then say there's 2 plus 4 H2Os. So it's going to be 6 H2Os on my left-hand side. That's going to form the O2 plus 4 H plus ions plus 2H2 plus 4OH minus. So now if they ask you what is the product, what are the products, you actually have 3 products, and you'll see this becomes quite important later as well. You've got 3 products. You've got oxygen gas, you've got hydrogen gas, and you have hydroxide ions. And this is quite, there's the chloroalkali industry that we do later in a bit of detail that actually uses the one of the water reactions for its products. What will be the oxidizing agent this time? Water. Yeah, please don't look at the products, still only water. So the oxidizing agent would still be water. But this time the reducing agent is also water, and that's okay. It can happen where the oxidizing agent and the reducing agent is the same thing, because water is giving electrons. Some of the water molecules are giving electrons, some of the water molecules are taking electrons. So it can be the same substance. Don't think that it can't. Okay. So that's why the water reaction is pretty important, because you are going to use it. So now, when we look at the table, we haven't actually spoken about those voltages yet. So those voltages that you see in the table, they are called they are called the electrode potential. So you see, that's why they call it the standard electrode potential table, the SEP table. So if we are looking at these voltages, this is actually the voltage that it needs for that reaction to take place. So if you don't send this amount of voltage, if I go back, I'm just going to use this one as an example. So if I go back to this reaction, because remember we said electrical energy into chemical energy, and voltage is energy. If you think back to the definition of voltage, voltage is W over Q. So this work done per coulomb of charge, this is the amount of electrical work that I must do per coulomb of charge. I'm not going to ask you the physics definition in the chemistry paper, but just think in the back of your head, voltage is energy. So these voltages that line really wants to keep on moving. So the voltages that they give you is actually the electrical energy that we need. So if we go and look back to our reaction that we used there for the chlorine and the gold, this was our 1/2 reaction there, and that was our other half reaction. Where did I cover it now? Is it below? Yeah. There's my Cl minus and there's my Au. Now you'll see on your information sheet, you're going to find an equation that says, or that tells you that there are some equations that we can use in electrochemistry. So I'm just going to copy them very fast for us. So you'll see on the chemistry information sheet, there's not a lot of formulae in chemistry, but there are some. Not as many as in physics at all. But you will see for this section, there's actually 4 of them belongs to this section. If you look at your chemistry information sheet, these are the ones that you will see there. That's tiny, and these are all for this section. So there you go. So you've got the equation there. I always use the top one, it doesn't really matter, because what you should know is that the cathode is where reduction happened, and that is the oxidizing agent. Remember, we got all of that from the half reaction, and this is kind of bring it all together, that the cathode is going to be where the oxidizing agent, the cathode is reduction, and that would be the oxidizing agent. Anode is oxidation, and that would be the reducing agent. So that is all, you can kind of, it helps you with your definitions, this equation as well. I always use the top one. E cell is E cathode minus E anode, because we have it here in our half reaction already. We have cathode and we have anode. So please write the formula down, because they want to see that you know that it's E cathode minus E anode that is going to give you the E of the cell. Now, there's 2 other things that's important. You'll see there's a little theta there. So that theta there means that it's at standard conditions. Now, these standard conditions are a little bit different to the other ones on your information sheet. Standard conditions here is room temperature, not 0 degrees Celsius. It's room temperature, which is 25 degrees Celsius. If it's a gas, that's still the same as for other things. It's 1 atmosphere or 101 kilopascal, but on you can just say 1 atmosphere. And if it's a concentration, if it's something that is AQ, then the concentration must be equal to 1 mole per cubic decimeter. So if it's not these standard conditions, the voltages would be slightly different. So in non-spontaneous, in spontaneous, these ones, electrolytic cell, non-spontaneous, they don't often ask you to work out E naught, because that's the electricity that you need. More often they will ask you for the electric energy that you're getting out, which is the non-spontaneous. Keep on stopping it. The spontaneous one that gives you energy. So E cell, the voltage that you need is always going to be E cathode minus E anode. So if we look cathode, which of these two was the cathode, the chlorine or the gold? Gold. Remember, we have it here. That's why I always say these half cells are so important, because we already wrote that reduction happens at the cathode. So I know that was my gold reaction, and you just put in your value in there, and it's 1,42 volts. So 1,42 for our cathode, and then we go and look for our anode reaction. So that's the chlorine one. So you're going to say minus 1,36. Okay, so this is a bit of a weird one that they gave you here. These values are very close together. So you're going to see that you end up with an answer that is actually positive. And normally, for a non, that's probably why they didn't ask you for this one. We're going to end up with a positive answer. Normally, when you end up with a positive answer, it means that these things would react spontaneously. So you can only do this when it's molten. And we'll get to that again when we do spontaneous. You couldn't have done this in water, because then they will directly react with each other. They wouldn't send it. They wouldn't need, this is actually a spontaneous reaction because the answer is positive. So you end up with a positive answer. But I just wanted you to see how to get the voltages. So we'll do it just now for one that doesn't give us a positive answer. A positive answer would point to a spontaneous reaction, which would mean that the gold and the chloride ions, if they were aqueous, would react with each other directly. They wouldn't need an electric circuit. But so this is a spontaneous reaction, but in this case, because it was a liquid, we could drive the reaction by using an electric current. But can you see where I get the voltages from? Okay. All right, so you will see for most of these, if I'm going to do it, so for water, let's just do it for water quickly, that you can see that we can do one where the answer isn't going to give us a spontaneous answer. So if we are looking at water, the values that so again, you would write E cathode minus E anode is equal to your E cell. And remember that this is at standard conditions. Always tell yourself that it is at standard conditions. So now remember cathode. Which one is that going to be? It's going to be water, yes? The top one or the bottom one? Okay, reduction is the bottom one here is losing electrons. So if it's losing electrons, is it oxidation or reduction? Oxidation happens at the anode. Reduction happens at the cathode. So which one will be the cathode one? Top or bottom? Both. So if you, okay, I see what you mean. Yes, so the bottom one of my reactions that I wrote down, yes. So this is going to be the cathode. So for our voltages, which voltage would be the cathode? The top one. Yeah, sorry, I forgot that I actually two things there. So it's this one is my cathode because it's reduction happening at the cathode. So it's that half reaction. So it's going to be minus 0.83 that we're reading off the table there at the top. And then minus the bottom one here, that is 1.23 positive. If it's positive, you don't have to write it, but just remember that the signs are important. So now we get minus 0.83 minus 1,23. Okay, you don't have to write it obviously twice. But now you can see the answer is definitely going to be negative. So it's going to be minus, what is it, 2,06, is that right? 2,06 volts. And that means that my negative answer here means that it is non-spontaneous, because with the negative answer, it's not a direction. Remember, energy is not a vector, it's a scalar. But it is a non-spontaneous reaction, but it means that it needs energy. So it needs electrical energy. And that points to the fact that it is a non-spontaneous reaction. So electrical energy is going to be converted into chemical energy. And the minimum voltage that you must supply to get this to happen. So your battery that you use must have a voltage of 2,06 volts to get this reaction to happen. Does the voltages make sense now? Okay, good. Yeah, that's the best way of doing it. There's a shortcut way of doing it. So if you draw a line between your substances, so there was our one water and there was our other water. So a very quick shortcut that you can use, especially if it's a multiple choice question. You draw a line between them. So you can see it's a negative value minus a positive value. So it's going to end up a negative answer always. So that's the best way of doing it. That is non-spontaneous. Your answer is negative, so it's going to be non-spontaneous. But the quick way of doing this is if you look at the slope of this line, it gives you a negative gradient. So that graph there is a negative gradient. So that, because it's a negative gradient, it's going to give you a negative answer, because it's going to be a negative value minus a positive value, which means it's always going to give a negative answer. So if you quickly draw a line between them and you get a negative slope, it shows you that it's non-spontaneous. Some people do that whole C thing, where you draw from this, if it forms, but the thing is it forms a C either way. So if you're going to draw from here, this one, this is the reaction that takes place, and this is the reaction that takes place. So if it goes from the bottom to the top, then it's non-spontaneous. But then the other way around, so if it was this way around, so if it is spontaneous, it still forms its CF, just forms it upside down. So the C method is actually confusing some people. So this is the proper way of doing it, saying it's negative, and therefore it is a non-spontaneous reaction. If we look at something that would be spontaneous, like from yesterday, so if we have zinc and copper, I'm just going to put a page in there with a table. Oh no, don't want that. Come, little table. I'll just show you quickly. So if we had our zinc and copper from yesterday, remember we had the zinc ions. We had zinc, and we had copper sulfates. We had copper ions. So we had the zinc and we had the copper ions. There it is. So now, if you look at those two, that was the half reactions that we had. We had Zn that forms Zn2 plus 2 electrons. We had Cu2 plus 2 electrons that formed Cu. And you can see that one is giving electrons, so oxidation is loss, reduction is gain. Oxidation happens at the cathode, reduction happens at the anode. Still the same, even though it's a spontaneous reaction, you stick to those rules count for everything, and you add up your reaction and you can do it. Now if you look at those values, there was my one reaction and there is my other reaction. So we already said oxidation happens at the cathode, so it's the zinc half reaction. So when you now write your equation down and you say E cell is equal to E cathode minus E anode. Now we know that the cathode was where? You see what I did? You should scream at me when I do nonsense like this. Oxidation happens at the anode. And reduction happens at the cathode. Yes, so now cathode is the copper one. So you can see here it's plus 0.34. So it's going to be plus 0.34 minus, and now we go to our anode and it's minus 0.76. So this is why this putting the signs in brackets is important. So minus 0.76. So you can see that you end up with a positive answer. So it's going to be positive, I think it's 1.1 volt. So that means when I let this reaction happen, it's a spontaneous reaction. And it can, if you put them together, they immediately react with each other. They'll probably show you this reaction because it's a nice one to show you in class. So it's a spontaneous reaction. So you can see the blue copper iron color disappearing, and you can actually see copper forming. You can see the metal forming. But now, shortcut, if I draw a line between these two substances, I had zinc and I had copper ions reacting with each other. So if I draw a line between them now, you can see here, the slope is positive. Can you see that? Okay, so like I said, some people will say you draw a C. But yes, if I draw, this is the one that happens there and this is the one that happens here, there. Yes, it does form a C. But if it was non-spontaneous, it would still form a C just from the bottom. So forming a C it will do. So that's why, yeah, even if it does, yeah, the other way around, this is proper. You can do it, and if you get a positive answer, then you know it's a spontaneous reaction. There are many shortcuts, like I say, that people can teach you, but this is the one based on the real base principles, so it will always work. All right, so now the only thing that that we can just practice now. So another one. So all you have to remember now is that you have to look for water as well. So that's what this page is basically telling us. If we took that aluminium, if we take aluminium oxide, for instance, I don't know what they're using here, it doesn't matter. Oh, it was aluminium bromide. You take aluminium bromide, you can see you've got the waters and the aluminium. So you need to decide which reaction is actually winning. So if you look at your table in this case, oops, what did I just do? Go away. If you look at your table now, you will see that on this side the water will win, but on this side the bromine will win. So it doesn't matter, you still just trust your table. So for that reaction, for this reaction here, you can see that the competition for the strongest oxidizing agent that would rather be reduced, so it will be reduction, would be either aluminium, which is there, or it would be water, which is there. And now you can see the stronger one is the bottom one, so that means water wins and aluminium doesn't happen. And if we look at our reaction on the other side, so this one was done for us in the notes, we can move to one that isn't done. So that's why they wrote down the water reaction and not the aluminium reaction. But now if we look at the BR is there and water is there. So now if we follow our magic sentence and we say it's the strongest reducing agent that would rather be oxidized, that would mean that BR is the strongest. It beats water, so that means water is not going to react, and that's why at the anode they wrote the BR reaction. Are you happy with that? Okay. So please remember the tests. The hydrogen is the one that explodes with this squeaky pop sound, and then the Oxygen is the one that makes something relight. Bromine, if you see Br, it's actually a liquid, and it actually forms a brown liquid when you do these reactions. Some of them you can do in class. They're a bit, bromine it's dangerous because bromine is poisonous, and if you heat it up to let it melt or something like this one, you can do. Aluminium bromide can definitely be done in class because you'll just see the water go color brown. But if it's the molten one and you have to heat them up, then it forms a gas, and bromine gas is not the greatest. All right, so here, so that would be product. So often in these reactions, they would ask you, what products do you see? So you'll see gas. You'll see a colorless gas forming on the one side, and you'll see please, if they say observation, is what you see. So don't say bromine forms. That's not what you're seeing. You're seeing it go brown. And especially for pracs, but I think you guys are done with chemistry pracs now, hey? Yeah, so, but just for future, if you see, if they say ask for an observation, is what do you see here? Taste could be an observation. All right, so okay, this one is super important. This concentrated copper chloride one is very, very, very important because the chloride is the only one where you have a bit of an exception happening. It's not. So I'm going to just do the copper chloride that we look at that one. So if we have copper chloride and it's AQ, we need to be able to differentiate between standard conditions and not standard conditions. So it says give the oxidation half reaction and reduction half reaction at the anode and the cathode for when it is standard conditions. So add the products. So let's look. If it's standard conditions. Okay, now remember, then we can use the table. Okay, this one is important because in the chloroalkali industry, we're going to refer back to this all the time. So for standard conditions, you just follow your rules. You've got CuCl2, and they tell you it's a solution, so it's AQ. So the three substances I'm going to look for, what are they? Perfect. Cu2 plus, Cl minus, and the AQ tells me I have to look for water. So I need to, you'll get so used to the water reactions. The two that we use, you can basically immediately go and highlight them because it's this one on the oxidizing agent side and it's this one on the reducing agent side. Those two are the two waters we're going to use. Did I do the right one this time? Yeah, on that side. Okay, now we're going to look for Cu2 plus, and there it is, and we look for Cl minus, and there it is. So if it's standard conditions, you trust your table, and you say the strongest, circling the wrong place, strongest oxidizing agent would rather be, and reduction, remember, is gain. So I can write my reduction half reaction, and that would be which one? Great. So Cu2 plus, you copy it from the table, plus 2 electrons. One-way arrow forms copper. Then we've got our oxidation half reaction. Which one would that be? Look at your arrow. Yeah, so for H2O, for this side, H2O is actually beating Cl minus. So the Cl minus is not the reaction that's going to take place. It's the H2O. So the oxidation half reaction now is going to be the two, very important, the 2H2O that's going to form O2 plus 4H plus 4 electrons. So those are your half reactions. So when you look at your products, the products is going to be copper and oxygen gas. Those are going to be your two products. But now if it's not standard conditions, and this is where you need to be very careful, and it actually really only works for chlorine, because the other standard potentials are too far apart for it to actually work. But what you will see now is if they are very, very close in value, so there is a cutoff. It's not in the SAGs, but if you look at the difference here between H2O, that's 1,2 and 1,3, it's very, very close. But here for water, you'll see that sometimes we use Na, and that value is bigger. The difference is bigger than 0.4. Then it doesn't happen. But what I'm trying to say is, if it's not standard conditions, if it's now concentrated, and that's what the question is going to say. Standard conditions, you trust your table, and that's going to happen. If they tell you that it's concentrated, and they are going to do that in the chloroalkali industry, which is a huge application of electrolytic cells, electrolysis. So if it is concentrated, what then happens is that because it's concentrated, it becomes a little bit stronger as a reducing agent, and it becomes a little bit stronger as an oxidizing agent, the ions that are now more concentrated, the substance. So I still am going to look for those same things. I still look for the water and the copper. The copper ions are now a little bit stronger, so they move a little bit down, but it doesn't affect anything on this side. So my reduction half reaction is still going to be the exact same reduction half reaction, because there's nothing else that could pass it now. So I still have Cu2 plus 2 electrons that forms copper. So I'm still going to form copper metal for my reduction half reaction. Remember, it's the cathode. At my cathode. Then my oxidation half reaction is going to be now. This is where it comes in. Because these are so close, the difference is less than 0.4. The chlorine becomes a little bit of a stronger reducing agent. So it moves up a little bit. And because water is so close, it passes water. So the Cl- is now a stronger reducing agent than what it was, because it's concentrated. And therefore, it is going to beat water now. So the oxidation half reaction is not going to be the water one anymore. It's going to be, so this is it's basically an exception. Because it is concentrated, it is now a stronger reducing agent, and the Cl2Cl- reaction that's going to form Cl2 plus 2 electrons is the one that actually is going to take place. So now my products is not copper and oxygen. Your product is going to be copper and chlorine gas will now be your product. And this becomes very important in the industry, because often they want to form chlorine gas or they want to form oxygen gas. So they can control what product they're going to form by controlling the concentration. If the concentration is low, they will form oxygen, lower than standard or on standard conditions. If the concentration is high, they're going to form chlorine, which is in the chloroalkali industry what they want to form. So you'll see in the for that application, you should actually just jump to it now, then you can see it. For that application, we want chlorine to form, so we use concentrated substances. Okay, so now all the rest of this chapter, so you know now how to use the table. You know how to use the table for non-spontaneous reactions and how to work out the voltages. So the rest of the part on non-spontaneous reactions is all applications. So electrorefining, so this is when you take stuff out of the ground and you now want to make pure copper out of dirty copper. So you've got copper ore and you want pure copper out of it, that's an application. If you want to plate jewelry with metal, so you have a piece of cheap metal and you want to cover it with gold or silver, it's called electroplating. It's just an application of electrolysis or electrochemical cells. Okay, so all of these are just applications. And one of the very, very important ones that I'm going to jump to, because it's what we just did, is the chloroalkali industry. So in the chloroalkali industry, why it's important is because half our world is covered in this stuff, if you think about it. Because what is NaCl? It's just salt. And half the world is covered with salt water in the sea. So that means we have endless sources of this. And the chloroalkali industry is then basically using salt water and producing these three things for us, which is chlorine gas, sodium hydroxide, which you don't know yet, but it's a very strong base, a very important base, and it's used in all kinds of cleaning agents, and hydrogen. But you're still going to use your table to get to these reactions. So they can still ask you. So now you'll see it's just an application. Because if you think about what we have NaCl. You don't even have to write plus water, because NaCl actually, so this part, I don't even know why we put it there, because NaCl is already in water. So you don't have, it's not reacting with water. It's just electrolyzed. So actually why they do it is because that's the balanced equation. So let's go and see. If we didn't have that and we just go to the table, and we trust our table and we trust what we know about redox already, and I just want it to be all on the page, there you go. And we look, okay, what do we have? We have concentrated, and because it's concentrated NaCl, they call this brine. You know, if you buy tuna in brine, it just means it's in salt water. So they call it brine. So it's concentrated. And that's the important part. So as soon as you see the word concentrated, it's not standard conditions anymore. So they can become stronger oxidizing agents and reducing agents. But you're still going to follow what we've done. You know we are looking for three things. The AQ always tells you that you're looking for water. What are the other two things I'm going to look for? Absolutely. Na plus and Cl minus. So let's go find them. Na plus is right there. Water is there. Then the other water is there. And Cl minus is there. But now remember what we said. The fact that it's concentrated makes them a little bit stronger oxidizing agent and reducing agent. But it will only make them about 0.4 stronger. So this one will just get a little bit stronger on this side because that's already 0.4. So a little bit stronger, but it's not going to make it past the water. So on this side, the water is still winning. But on this side, the Cl minus is going to be beating the water now because it's going to take it up about 0.4. So if you go up here, it's going to take it up about to that point there. So it's going to take it all the way up around there. There's not a dead fast rule because it also depends on temperature and stuff. But about there. So it takes it up a little bit. So now you can see on this side, water is still winning. And on this side, water is going to still be winning because we're looking at our arrows. Increasing oxidizing agent will be reduction. Reduction is gain, and it happens at the cathode. So my reduction half reaction and my oxidation half reaction, I can still write them down. Reduction is going to be this one, the water. So we're going to have our 2H2O plus 2 electrons forms H2 plus 2OH minus. Because the sodium is now the spectator ion because it's not actually taking part in the reaction. It's the water that reacts. on our oxidation side, can you see? So it's not going to be the water because Cl is now stronger. So it's going to be the Cl minus. It's going to be the two Cl minuses that's going to form Cl2 plus 2 electrons. Oh, remember water is a pure liquid. Pure liquids doesn't have a concentration. So no, water is, because it is a liquid. Remember when we did equilibrium? Water doesn't have a concentration, so it can't get stronger now. Okay, so it's just the ions that become, so it's only when it's actually really only going to be chlorine that is ever going to beat water because it gets more concentrated. Because if you look at the water reaction, there are not really fluorine. Let's just look at fluorine here. Fluorine is all the way down here. So if you want fluorine to pass water, it has to go all the way up there, which is way too far. Can't do that because of the other factors. So the only ion that can actually do this thing where it passes water is the chloride ions. There's nothing that the IEB, it's going to be something that's not in your table. So for the IEB, there's nothing in the table that can do this except for chlorine. So look out for the chlorine one because that's the only one really. That's why I said it's kind of an exception. But does that make sense? Okay, so now we can write our net ionic equation and you can see that it's 2H2O and this is why our reaction had the water in it, plus 2 Cl minuses, the electrons cancel nicely out again, forms H2 plus Cl2 plus OH minus. Now, when we look at the products of the chloroalkali industry, you will see. If I look at those three products that we spoke about just now, this is like a huge industry. So they say millions of this stuff is produced. It's Cl2 that you can see there it is. It's H2 that you can see there it is. And the other substance that we form is NaOH. Now in this reaction, I already have the OHs that formed. So where did they get the Na from for the NaOH? Remember what we started with? We started with NaCl. The Na ions didn't react. But they're still there. They're swimming around watching this whole situation because they're spectators. But now, because they are positive ions, what will they do with the negative ion? Attract. So those are the only ions left. So those two ions will attract each other. And that's where the third product, the NaOH, comes from. So the chloroalkali industry, which is a very important industry in the world and produces chlorine gas, ammonia, sodium hydroxide and hydrogen gas, that this is the reaction that it's based on. And you can see it's just an application of the of electrolysis because it's just, you can see that's just what happens. Now, in the old syllabus, you had to learn 3 of these different cells for the chloroalkali industry. Before I go there, they can ask you a use of these products. Just know one of them. All of us know that chlorine is used to purify water. It's used as a bleach. It's used as a disinfectant. You can learn any of these. They will never ask you more than one. So for chlorine gas, those are the uses of chlorine gas. Sodium hydroxide, because it's a very strong base, they do use it to clean things. They also use it for paper. And hydrogen gas, they use to, you can say for explosives, we tried not to put mean ones in here, but hydrogen is used for explosives. And then it also is used to make ammonia, which is very important in the fertilizer industry and fuel cells. I'm hoping that the world will one day just run off hydrogen, so because it's very clean power. So to make fuel cells is also, hydrogen gives you clean power for fuel cells. So make no one of them. So yeah, there were three of them. There was the membrane cell, there was the diaphragm cell, and there was the mercury cell. The diaphragm cell used asbestos in between the two things. The mercury cell, we know mercury causes people to go crazy, so it's poisonous, so they don't use the mercury cell anymore. So the only one that you guys need to learn now still is the membrane cell. And why we need a special cell for this? I'm sure here's the diagram, yeah. Why we need, is this the mercury one? No. Why we need a special cell for it is because these two gases that forms out of this industry is not poisonous, they are poisonous, but that's not the whole big thing. That's not the whole big problem. The problem with these two gases, we're forming chlorine gas and we're forming hydrogen gas. Now remember, hydrogen is in group 1, chlorine is in group 7. They would love to get together and swap out electrons. They're very, very reactive when they meet each other. And that is why we can't just make them in the same container, besides the point that it will still be mixed. We can't make them together because they will explode when they touch each other, and we don't want that. So in the industry, so this is the only one you need to know, this membrane cell, they split it up. So there's still salt water here. So you still have NaCl, and you can see that NaCl comes in here at the bottom, concentrated NaCl. The Cl- ions goes to the positive electrode. Chlorine forms, like we just said in our reaction here. Chlorine gas forms, exactly this half reaction takes place there. And then on the other, the problem is if all the chlorines are used up, then water can start happening and I can form oxygen, and again, I don't want oxygen to form here because oxygen will also react with chlorine gas and make a big boom and react, and even would hydrogen react with oxygen. So we don't want oxygen to form at all. Even by accident, we don't want it to form. And that is why they put a ion selective membrane. So this membrane only allows positive ions through. So they charge it. Okay, they charge it negatively. So if it's negatively charged, it repels the Cl- away. So the Cl- stay on its own side. And it also prevents other ions from going through so that we don't have oxygen actually forming on this side. So we want only the sodium ions going through. So sodium ions go through, and then the sodium ion is in competition with water, and the water wins. So the water forms the hydrogen gas, which is collected on this side, and then the sodium ions are just swimming around, but that's nice because as soon as the hydroxide ions are forming, they combine with the sodium ions, and that is what gives us our NaOH as our last product. So this membrane cell is now the only one that you need to know, and basically the only thing that's important